Hello, Flat Earth researchers, debaters and debunkers. Just having some thoughts about the whole globe Earth belief, and as always trying to kind of consider ways in which people can be helped to understand how someone who realizes we're not on a spinning ball Earth can actually arrive at that understanding. Now, of course, we are taught to think that we're quite smart for being able to perceive ourselves from this kind of external frame of reference, and we are taught to believe that we're kind of being humble in a way. We are humbling ourselves with this ability to understand that, oh, we are just kind of a minute ant-like creature on the surface of the Earth, and then all those, amongst all those billions of people, and we're just a speck among billions of other planets or whatever. Of course, it's a mistake to, in the first place, think that we are on another planet. But what it is it's actually the globe Earth belief is a very egocentric thing. Whereas someone who realizes that we're not on a globe simply because of observations is able to see things literally from another person's perspective. So think about this, if you're, the idea we're given of what we see when we look across the Earth, if we draw a circle and we see someone, it's either illustrated as someone looking into a bulge of curvature. Well, that's pretty much about it, isn't it? Yeah, I mean, that's the way it has to be illustrated, isn't it? Or even if you are a person illustrated on top of the globe, or just a circle, if it's illustrated on paper, then of course you're told that you're looking down. We don't actually look straight ahead. Now, fair enough if you want to say that, your eyes aren't good enough to be spot on with looking directly ahead, and you can say your eyes are drawn to the horizon, which, if you take a photograph and that camera is level, that horizon will be at what you can call eye level, in the center of the camera's field of view. All right, there is no denying that. If you have the camera, say, 1 or 2 meters off the ground, looking across a flat surface, whether it's the sea or whatever, or if you want to say that it's a locally flat surface, where everything converges, where the sky and the surface appear to converge in the center of your field of view when you're looking straight ahead, is pretty much, that's eye level. Okay, if you want to argue about degrees, there's no way you can actually do anything to prove that. You can only assume it. So given that, the whole thing though is that your understanding from this is that regardless of, you're kind of ignoring the way perspective actually allows us to see things. It just, it looks flat, so it is. But you rarely ask the question, why does it look flat? Well, because you look across a flat surface, and if you look directly across a flat surface, that surface will appear to be at your eye level. There's a point where there is, a horizon where everything, the surface in front of you ends up getting more and more condensed until the entire surface in front of you just doesn't go any higher in your field of view because it is flat. It takes up half of your field of view. In fact, this is a natural thing that tells us which way is up. It's obvious. It helps us balance. However, that aside, what we are told to believe or perceive when we're looking at a horizon is that the horizon is, as I mentioned earlier, it could either be considered as a bulge, which is kind of ridiculous. Let's just go with the idea that it is curving away. That seems to be the most commonly accepted idea, because we've got looking at things that appear to drop in the distance. That's the claim. You can't see the bottom of the ship because it's dropped down the curvature. Okay, so let's just go with this assumption that when you look across a locally flat surface, you are seeing some kind of curve down from your perspective. Okay, so that means basically that if you then put yourself in someone else's shoes, that is someone who is beyond your horizon and below your original horizon, that person is at a lower elevation than you. Doesn't matter how you want to illustrate it, doesn't matter how you want to perceive the Earth as a spinning ball in space, that doesn't matter. Even if you want to say, well, you know, there is no down in space, the thing is we're talking about on the Earth, our direct experience as human beings on this Earth with the physics, with the actual physics that governs our existence. So you're looking across a large vista, whatever it might be, a flat plane or water or whatever, it doesn't matter, or even, you know, something that eventually gets so small you can't see it, and it's, you know, just there. It becomes, everything becomes part of the horizon. But essentially what you believe is happening in your vision is that at the limit of your vision, where everything appears to curve, the Earth is curving away from you. So anyone who you can't see, or even maybe you can see them, but half their body is cut off by the horizon. So it means, what you're basically implying is that the person's feet that you can't see because of your personal horizon are below, physically lower than your feet. Okay? So whether that's 1 mile, 2 miles, 3 miles, 10 miles, doesn't matter, because the physics doesn't change. So what's happening is, you know, if that person, let's say they could appear to be a meter lower elevation than you. So if you ran a tube or a pipe or whatever of water from your elevation, could be whatever, waist height, head height, from your feet, doesn't matter, to the other person's feet who appears to be lower than you, then the water will run to that person. The physics dictates that this person at a lower elevation, regardless of how you suddenly want to jump out of this reference frame and consider it as being a ball in space, doesn't matter, because we're talking about reality. We're not talking about models. We're not talking about perception or, you know, the ability to see yourself as being on a globe. We are talking about the physics of reality. The physics of someone being physically lower than you at a lower elevation, a lower altitude, whatever. Downhill, essentially. And that's it. That's all you've got to think about, is because the thing is, if you go and be that other person, they're going to see the same thing. When they look at you, they're going to see that you're lower. You're at a lower elevation. But the way you see them is that they're at a lower elevation. Hang about. That doesn't work, does it? How can you both be lower than each other? Well, if you were both lower than each other and you had a tube of water in between, then okay, the water would maybe gather at each end, and there would be a gap of water in the middle. Either way, you can do a thought experiment, or you can do it on a meter or 10 meters. the physics doesn't change. Now it's funny because I had someone show me a thing about how the Romans did their aqueducts, and they basically, their claim was that water goes uphill. Well, yes, it does, because what happens is you know, so the guy has this tabletop thing where he's got the main reservoir on one side of one end of the table, and he gets some, and there's a reservoir, and it's high up, and then there's a tube going from that reservoir to another reservoir, and the second reservoir is about half the height of the first one, or maybe 2/3 the height, whatever, it doesn't matter. It's slightly lower than the top of the other one, but it is still elevated from the top of the table. Yeah, do you see what I mean? So two ends, one funnel end is high, and the other funnel end is lower, but obviously both of these things are on a tabletop, so they're both higher than the tabletop. So when the guy pours in this wine into the one on the left hand side, the tall funnel, and then sends it down the tube, along the table, along the tube, there's this aqueduct, and then of course the tube it then goes uphill a little bit to the reservoir, the second reservoir, which isn't of course as high as the first reservoir, but what you have is water going uphill. You know? But so this was basically the way this glober tried to say, well look, water goes uphill. But of course, you know, it's just such a straw man argument, because no, the water isn't going uphill any higher than where you first put it in. It's still lower. And it's just like, you know, these are the kind of ridiculous arguments these sophists have got to come up with. Because they know. All they have is a model of excuses and explanations. A model that does not fit reality in any way, shape or form whatsoever. They say it's a model that represents reality. No! And even if you want to talk about flat earth models, then no! What we have is reality. So, how do you model reality? Well, you do something like that tabletop thing, where you pour water in at one high level, and it will go down along the table horizontally, and it will go uphill slightly, but it will never, ever, ever go higher than the original level that you poured it in. Won't happen. Oh dear. Someone asked me the other day, if you had all the resources, you had all the money in the world, you know, to go and prove flat earth, what would you do? I'd say there's no need. Water proves it. All you've got to do is think about it. Think about all the properties of water. Think about, okay, gravity. The more mass something has, the more gravity is supposed to act on it and create a greater force, and therefore create a greater weight. So, you know, 1 million tons of water apparently has, you know, all this force, 1 million tons worth of force acting on it, making it 1 million tons. So in that case, huge bodies of water shouldn't be going anywhere, because gravity should be sticking them all in one place. They shouldn't be able to flow. Yeah? It's really simple. You know, you should actually be able to create a column of water, because you just think about it. You get a tank. The bigger you make this tank, the more water you can hold on it in it. So you're all right. You got, you know, 1,000 tons of water in a tank. So there's so much gravity pulling all that water down that you should be able to take the walls away from that container, and ta-da! That 1,000 tons of water will just stay there. pulled down by its own gravity. It won't move. It won't spread out because it's such a big mass. Gravity's got such a strong hold on it. Can't go anywhere. But what happens, of course, is the more water you have, the more pressure, the more that water is just going to come charging out if you release it in any way. It is just a total oxymoron. Totally ridiculous. All right, thank you very much.
Click subscribe and the bell icon if you'd like to receive notifications of new videos from Phuket Word.